Good afternoon, ladies and gentlemen. This is our first video on magnetism. Now, I know many of you have done a lot of work before, so I want to explain it because I got some feedback that it's better when I teach it. So look at this rock. How is this rock magnetic? Look at this horseshoe magnet. It is attached to these pins. So let's see what's actually going on, shall we? More than 2,000 years ago, people living in Magnesia, Greece, discovered an unusual rock. This rock attracted materials that contain iron. You guys know now there are only 3 metals that are magnetic. Can you tell me what they are? So the 3 metals that are magnetic, we know, are on the periodic table, and they are in alignment with each other. They're right next to each other. The first one is iron, then cobalt, then nickel. So there must be something about these 3 metals that make them magnetic. Well, this rock itself is magnetic because it has this mineral called magnetite, and there's a property in magnetite that makes it magnetic. Let's find out what it is. All right, so in our classroom, we would have used 2 different types of magnets. One is a horseshoe magnet, and we can see how it's bent. It has 2 little letters on it, an N and an S. We could also use bar magnets, an N and an S. If we go back to school, I bought so many fun things for us to use. I can't wait for us to play around with the magnets. And you know what? We're still going to play because you need to see this in person. All right, so there are several materials on this side: aluminum, plastic, iron, steel, gold, and cobalt. Which ones are magnetic? Well, the only ones that are magnetic are the ones that I just told you: iron and cobalt. Gold is not, however, steel is, because steel is an alloy. And what that means is that there's more than one metal in steel. And there's actually carbon in steel as well. Steel is not a pure compound, it's actually a mixture. So you can separate out the carbon and you can separate out the iron in steel. But because steel has iron, it makes it magnetic. So there are lots of things that are magnetic if they have iron in them, or cobalt, or nickel. Your regular nickel, if you took a nickel and tried to place a magnet next to it, nickels are not magnetic. So if you went to the beach and you took a magnet, you wouldn't find any money. Why? Because money is not magnetic. Nickel is not really made with nickel anymore. And that's it. All right, let's go back. Each end of a magnet is called a pole. So the poles are north and south. Characteristics of magnets. All magnets have a north and a south pole. Those are the 2 pieces that have that attractive force. Now, magnetism is a non-contact force. It's invisible. It doesn't need to touch anything. The magnets are the strongest at the poles. So this is iron filings, and this little iron is so difficult to get off. Now, I don't remember, if you guys remember, in the beginning of the year I asked you to use a tissue to try to separate the iron out of the solution, because if the iron got onto the magnet, we couldn't get it off because the attraction is so strong. All right, so let's do a little practice question, shall we? This is a magnet. The letters A, B, C, and D represent locations on the magnet. They're asking you which location has the greatest magnetic force. So if you recall, magnetism is the greatest at the poles. So the only letter that is the closest to the poles is letter D. Letter B is straight in the middle, so that's the same attractive force. A and C are equally distant from the north and the south, so those have the same magnetic force as well. But letter D is right at the south pole. So letter D has the greatest magnetic force because it's at the south pole. If we put something here, it would have the greatest magnetic force as well. Now, somebody in our class had stated to me that they thought they read that the North Pole has a greater attractive force than the South Pole. I don't believe that that is so because the Earth is a sphere. And the reason why we have magnetic forces is because the actual Earth itself is because the iron core is spinning. When the iron core spins, we know that iron is a metal. What does it release easily? You know that the periodic table has metals on the left, and all those metals are electron donators. So our magnetic core is spinning and releasing electrons, and that is why our Earth has a magnetic shield. So the North and the South Pole have an equal distance from each other, well, from the equator actually, or from the core. So they both have equal strength. So I'll do a little more research to see who wrote that. But sometimes we can't believe everything we read on the internet. So be careful. All right, so what happens if you break a magnet? Do you lose magnetism? Is it done? You drop the magnet on the floor, it breaks in two pieces. Guess what? Now you have two magnets. So if you break a magnet, now you have more than one magnet. So the South and the North Pole actually break apart, and now you have South and North, South and North. So this would be attracted to each other, but these two pieces would be repelling. Each piece would have a North and a South Pole. Now, I don't really like this picture because it's not really going to happen like this. It's going to go South, North, North, South. So you try to put them together where you broke them, it actually repels each other. And we would have done that in class too. So when we go back to school, break some magnets, and you'll see you can't put them back. They flip over. So this is actually not a good picture. I should maybe make this over again. However, the statement is correct. If you break a magnet, you get more than one magnet. And each piece will have its own North and South Pole. All right, let's look at this picture. We have arrows, and we know arrows represent force. Magnetism is a force. The North and the South Pole have two arrows because they attract to each other. So if you put the two magnets next to each other, they would attract and they would pull toward each other. So I wrote up a lab for us as well to show you the magnetic strength. And I bought these really crazy magnets. You could put them on your hand, and you could put them on both sides of your hand, and they would stick. It's pretty cool. Like poles repel. Like poles repel, so therefore, these two magnets, when you put them together, would push apart, almost like magic. So repel is a push, and attract is a pull. What's going to happen in these magnets right here? You have two south poles. This says repel, but why does it repel? Because they are the same poles. South and south repel. They have a pushing action. The north and north are going to repel as well. They have a pushing action, and the south and the north will attract. Opposites attract. All right. If you'd like to do this brain pop, it's extra credit. Magnetism, look it up. This is the coolest thing ever. I bought these little boxes for us. This is amazing because you can't see the magnetic force, but you know it's there because you can make things happen. Like we have doorbells that use electromagnetic energy. Elevators use magnetism. Lots of things in your world use magnetic force. Your computer uses magnetism as well. Now, we can't see it, but we know it's there. So how do we prove it's there? We have to use something that's magnetic. So these little tiny iron filings are magnetic. And if you sprinkle them, they actually will curve around to the other side to show you the magnetic fields. So these little lines are magnetic fields. They're invisible. Notice how most of the iron is on the South Pole and the North Pole. Why is that? Because the poles are the strongest. All right, magnetic lines of force. You see the lines, they connect. The opposite will connect to each other. So that's when they go around to the other side. Around to the other side. This is exactly what the Earth looks like, except we're not a bar magnet, we're spherical. So this shield protects us from all the ultraviolet radiation and gamma radiation. It doesn't protect us from all the ultraviolet radiation. A lot of it gets in because ultraviolet radiation is a short wave, but it protects us from gamma, X-ray, so that those waves cannot get in. All right, let's see. When you have two magnets that are the same next to each other, the poles, they do not connect. You see how they're not making a bridge. However, it's making a bridge to itself. Do you see this? This is showing you that the north and the south do attract. So whatever's around here has some kind of magnetic field, but when you put them in this direction, they're going to push apart. You can prove this with the iron filings. You can see how the iron filings are connected here, and there's a gap here because these two sides repel. So this is the reason why this is red, so you can tell what side is the north or the south, because in logic, you really can't tell if that's north or south. So if this was a bar magnet that was just black, you wouldn't know if there was the North Pole or the South Pole. How do we know? We have to actually use the Earth to determine what it is. All right, so this is a study jams video. This is a good one to review if you still are confused on this and you want a little extra practice, or you know what, you really need to assess yourself. You need to test yourself on your own. So I put a lot of quizzes on there on Google Classroom, so you could use them, or do this study jam. So you just go into studyjams.com, type in magnetism, and test yourself. Okay, this is my favorite thing because the Earth is like a huge magnet. So this is how you can tell what side of the magnet is the north or the south. So you hang a magnet by a string, and it's going to turn until its north pole points north, because the north is seeking the south. Wait, what? The north is seeking the south, and it's pointing north? I'm so confused. Our Earth is a great big magnet, but here's the funny part. Our North Pole is our geographic North Pole. That means Santa Claus lives here at the North Pole. It's the north side of our Earth, meaning you start at the equator and you travel upwards, and that's north. However, our magnetic sphere is the opposite. Why is it the opposite? Why do people call this the North Pole and this is the South Magnetic Pole? Why are we all confusing everybody? That's so dumb. Well, it flips. So it's never been the same. So every 50,000 years or so, the South Pole flips over and goes back to its normal position. Guess what? Right now, the South Magnetic Pole is where the North Geographic Pole is. We're going to flip. What does that mean if we flip? Well, I don't know what that means because we haven't flipped in anybody's lifetime. Humans haven't been around the last time we flipped. Really? So then how do we know we flip? Come on now. We use evidence from rocks. So rocks can have iron in them. They can have cobalt in them because those are minerals, and they can have nickel in them. They line up in a certain direction. And if you look at the layers of the Earth, they kept changing their direction. So the further down you go into the center of the Earth's crust, you get different rock layers in different positions. So the magnetic field flipped around. So right now we have the South Magnetic Pole. So our South Magnetic Pole is up at the top of the Earth. Look at it. It's straight directly in the center. But our Earth is tilted. So our North Geographic Pole, see this line, this red line? This is our North Pole, and that's our South Pole down here. But our North Magnetic Pole is right here, and our South Magnetic Pole is right there. Pretty cool stuff, huh? All right, so here's another picture showing you that our magnetic pole is down here. What does that say? North. But our South Geographic Pole is down there. And the same thing up here. So our Earth is a great big magnet, but the South and the North have flipped. So today, if you took a magnet, the North Pole will point to the north because it's attracted to the South Pole. See that? North and South are attracted. If we flip, and this goes back to normal, north to south, then the south would be attracted to the north. So right now we know that the South Pole is up there because opposites attract. All right, so what actually causes magnetism? Well, as you know, all matter is made up of atoms. Now, atoms have to line up in a specific arrangement in order to make compounds. So in this magnetic material, all the atoms are lined up. They're all facing in the same direction. So that means they all can participate in the tug of war in the same direction. If they're not lined up, well, a force is a push or a pull. They're pulling and pushing in all different directions, and nobody's winning. But here we are. We're all lined up together. We're all going to work together. So in a magnetic material, we have to be pointing in the same direction. These little things are called domains. In an unmagnetized material, the atoms are not lined up, and they're pointing in different directions. See all the domains? So this is pushing against each other. This is attracting. This is pushing against. These are pushing against, attracting. Nobody's winning because they're all different. That's not magnetized. Tell me why. Tell me why this is not magnetized, but this one is. Think about it for a second, please. Good job. This is magnetized because all of the domains are working together. This is unmagnetized because they're working apart. They're all working against each other. All right. That is our little movie on magnetism. It was a little longer than I expected, but you know what, guys? Pretty impressed that you watched the whole thing. Good job. Hope now you understand why things are magnetic.